Hi, my name is Josh Walgenbach. I work at Indiana University. I wrote the initial UID mapping implementation that's currently on our data capacitor WAN project. That's been in production for a while and doing good work. And I'm going to talk a little bit today about the work we're doing to expand and extend on what we've done and how we're trying to take that work to the next level. So, Lustre WAN. Since 2008, we have been providing a WAN file system to the community at large. It doesn't require any changes to the client file system, and it supports 1.4 up through 1.8. For us, well, for me anyway, my feeling is that for sharing data, the file system is the most natural user interface. When you want to share data, you want to basically say, mount the file system, look at the data, look at it using whatever application you want. For everyone who has used a computer, they've used the file system. So if the file system is the natural user interface, we need it to provide reliable data transfer, and we need it to be efficient. We need it to run applications across the wide area network without actually having to transfer every little bit of the data, only the data that's necessary to do the calculations. So to do that, we have to do some very specific things because Cluster A and Cluster B are run by completely different people, completely different organizations. You have a heterogeneous namespace, and more importantly, you have a heterogeneous UID space. So every individual user is represented by a different number. So what we did is we implemented a Lustre server kernel module that allows us to input maps from one place to another and translate those. UID mapping really grew out of the concept of root squash, where translating UID 0 to a squashed UID like 99, it's not that big a conceptual leap to do a one-to-one mapping of whoever needs to use data on your file system. We've had really great success using this, and because we were riffing on the idea, it had some limitations. Most specifically, it exists entirely on the metadata server. So unfortunately, that causes us to not support quotas. That being said, it's given us some time to think about it, and because of the changes to the code layout in Lustre 2, we have an opportunity to go back and make things right, the things that we couldn't necessarily have done, specifically fixing quota support. And because Lustre 1 didn't actually have a security model, we can go in and we can use the security model that's been introduced in Lustre 2 and use it to extend our work. So about a year ago, we came to the OpenSFS with these ideas, and we made a proposal, and they agreed to fund our work in two parts. To rewrite what we currently have, we're going to implement a static UID mapping module for Lustre 2, and we're going to extend GSSAPI to provide a shared key security mechanism. Primarily, well, I'll get into reasons in a little bit, but it's primarily because not every place that we partner with runs Kerberos, and there are other problems with running Kerberos in our environment for batch jobs. Okay, so what we currently have in UID mapping on the data capacitor WAN is it's encapsulated in its own kernel module, so it limits the number of places it touches Lustre proper. Mapping happens only on the MDS. The maps are managed by a proc interface on the MDS, which works, but is not exactly where I want to be doing most of my system administration. Mapping only applies to the TCP networks, and that's primarily a limitation of that's all I had to work with at the time. And the maps are indexed by NID ranges. We can make that better and more efficient. And as I said, it unfortunately does not support quotas. So the new UID mapping model that OpenSFS is supporting us to build is going to change things to make them more efficient and to fix some of our current problems. Changes in the Lustre code will still be restricted by making most of our changes in a separate kernel module. UID mapping will no longer be limited to the MDS and will provide quota support. This necessitates us to do UID mapping on the OSS nodes as well. Apart from that, the management server is going to hold the canonical copy of the map and update the MDS if necessary in the OSS servers with the current map and keep everything in sync so that no one's infringing on someone else's quota should that ever come up. To do this, the update method is going to borrow heavily from the imperative recovery table that Eric talked about, I guess, last year. And I'm great artist steal, right? I'm trying to steal as much from really smart people as I can. And I'm going to organize mounting clients as clusters so that I can apply sort of UID policies to them as a whole rather than individually indexing them as sets of UIDs. So to get here, I need to talk about clusters. When we build systems that mount our Lustre file systems, we don't think about them as 1,000 individual machines. We think about them as groups. We think about them sort of as whole cloth. And what I want to do is I want to apply policies to the clients sort of in that same method. So what I'm doing is I'm defining a cluster as a partitioned set of UIDs that share a common UID GID space. It's basically saying these sets of nodes are, for all intents and purposes, one machine, and I'm treating them that way. It's really convenient to think about them mounting it, and it's also a convenient way to identify how I want to map their UIDs. So when a client connects to a server in my new model, part of the process of initializing that is going in and taking that client's NID and looking it up and basically categorizing it into the proper cluster and then keeping a pointer to that cluster in the export structure. This allows me to very quickly reference everything I need to about that cluster, including reverse and forward UID and GID maps. So essentially what I'm doing is I'm playing the computer science trick of no problem can't be solved by adding another layer of abstraction. In doing this, I will have to change some of the way that ID mapping currently works in Kerberos. Right now, when the GSSAPI Kerberos ID map comes in, the GSSAPI portion maps the principal to a UID in sort of a timed way, and then every export for every OST keeps a copy of the UID map. So if you have large numbers of clients and large numbers of users all mapping, you can actually sort of exhaust memory. So the way I'm doing it actually reduces the amount of memory that I'll need to keep on the servers at any given time consumed by this mapping function. Here's a structure of what I'm envisioning the cluster to look like. Now, the canonical cluster is going to live on the metadata server. Sorry, I'm just checking my time. Okay. The canonical cluster is going to live on the management server, and if you can see, I'm sorry that the fonts are sort of small here. There's a version ID for the whole cluster, and only the latest one on the management node is kept on disk. Everything else is kept in memory. So for every cluster, there's a cluster name, and then there's the unmapped UID, essentially the squashed UID, which most people on Red Hat end up setting to 99 for that, and the GID. Flags about the cluster, whether or not it's a trusted cluster. Do we even need to map it? An admin cluster, do I allow root 0, UID 0 access? And those sorts of things. Then I keep essentially a range list, which is a linked list of NID ranges, so I know how to appropriately categorize an incoming client. And then 4 sets, well, a set of 4 trees that I'm using for forward and reverse mapping. And that's all kept in a linked list on the management node. To update the server, to update the servers, when OSS and MDS nodes come up, they obtain a shared lock on the cluster table, And when that cluster table is updated on the management node, it performs the callback that's given in the lock and tells the MDS and the OSS nodes, hey, I'm changed, you need to update me. The MDS and the OSS nodes present the version number of what they have in memory, and then the management node calculates the differences between the current map and the map that the server currently holds and only passes the delta. Like I said, this borrows heavily from imperative recovery. Here is sort of the timeline of the way this works, because even when I say it out loud, I get lost. MDS node comes up, cluster table lock is obtained, and passes back. And when it's updated, it calls the callback. The callback triggers the server to pass back the version information, calculate the difference, and return the table. I think it's much easier to look at it graphically. And you know, even the visualization is heavily borrowed from other places. So that brings us to the security of the system. And to talk about the security of the system, first I need to talk about trust. Ultimately, the file servers have to trust their clients. There's no way around it. They present any authentication credentials, they pass the data back, and if the authentication credentials check out, you have to believe them. Now that comes with trusting the admin. You have to trust that the admin isn't going to let the server be compromised. If the server's compromised, there's not a lot you can do about it. There is nothing we can do to protect a client from itself. The only thing you can do is mitigate the risk and protect one client from another. And that's unfortunate, and I've spent a lot of time, and certainly lots of people far brighter than I have spent a lot of time trying to figure this problem out, and it just doesn't work. Even if you have user authentication credentials, rooted is rooted. Those credentials are then compromised, and the person who compromises your system can assume them. So what I'm saying is that user authentication doesn't actually provide me with an added layer of security, but what it does provide me with is timed UID mapping, which in an interactive environment works really well. So in extending it, I look at extensions to GSSAPI. If you look at Lustre, you don't really have native Kerberos inside Lustre. What you have is native GSSAPI, which uses a Kerberos mechanism. So you can look at GSSAPI as a vacuum cleaner that currently only has one attachment. I don't want to ditch the whole vacuum cleaner, but what I want to do is add an attachment that fits my environment. So in the existing GSSAPI mechanism, which is properly GSSAPI Kerbe 5, when you look at it, not everyone runs Kerberos, and certainly not everyone wants to do cross-realm. Kerberos's greatest strength is also its greatest weakness in this environment. In my environment, when I submit a job, it could run for 30 days. I can't have credentials that hang around for 30 days. I don't know when my job is running. My job could run in 30 days. So am I going to make my users log in and keep their credentials current? The ways around this are you can have a key tab for the user, and that's essentially writing the password down in a file on the file system. I don't want to do that. Well, then I could have extremely long timed credentials. Well, I don't want to do that either, because then whoever compromises my system also gets those credentials. In this way, Kerberos doesn't actually provide me with any security, and it actually makes my user's life harder. So what I want to do is just stick with static UID mapping and just authenticate the machine so that I can solve very particular problems. I want to do machine-to-machine authentication so that I can ensure that who is passing me the message is the person that I think they are. I want to make sure that the data they're passing me is what they think it is. and I want to protect the data on the wire from encryption. All of this protects the machine from a third party, but does not protect the machine from itself because it can't be done. To do this, what we've proposed with OpenSFS, and they've agreed to fund, is the implementation of a shared key mechanism within GSSAPI in the kernel. The shared key mechanism can provide a hash machine authentication code so that we can authenticate machine traffic, we can authenticate one machine to another, and we can also use it to provide encryption. All of these things are functions that are provided by GSSAPI, but we have to provide the proper backend for it with a mechanism, and a shared key approach will allow all of these. Now, I'm not the sort of guy who can come up here and say that I can implement the cryptographic algorithms myself. That would be insane. So we're using the Linux crypto code that's already there. And in fact, for the GSSAPI mechanism, rather than using me to be the programmer, we went out and got an actual security expert who has contributed to the MIT Kerberos project and has all of the proper credentials to go in and vet this approach and make sure that we're not doing anything dumb. That's Andy Cordy. He's the Indiana University security officer, and it's not on the slides, but I totally should give him props for being a great guy and agreeing to doing this and having a brain the size of a planet. So this gets me to my conclusion. We developed a lightweight UID mechanism to share data in a very natural and easy way for researchers. Secure networks and producing a homogeneous UID environment are the two requirements to securely manage your identity in the form of who you are to the file system. Now, I know that sometimes a lot of our work is done in sort of the name as we do WAN stuff. But what we found is that this work, especially the UID mapping, is far more useful even on campus. We have researchers in departments where they have clusters, their own UID space. They're certainly not using anything like a centralized authentication system. But they still want to transfer their data onto a shared file system so they can compute against it in using our big clusters. An example is we have a guy in our biology department who's writing directly to Lustre from an electron microscope and then instantly gets to compute against it. We have machines in the astronomy department that are doing this, where they are using their own resources to compute and ours. So we are giving researchers the ability to use every resource at their disposal to try and get their work done, and we're trying to do it in a way where we simplify it and basically get out of their way without putting their data at risk. So the funding from OpenSFS is going to allow us to continue this work, and the timeline we have on this is about a year. So in a year, I hope to be here telling you how close it is to being in a place that you can download it and use it. And that brings us to my thank you slide, because nothing I've ever done has been done in a vacuum, and certainly nothing like this. I have to thank Steve Sims and the rest of the team I work on at IU, and certainly the director and dean and vice president all the way up. Kit Westneat, who is DDN, then NYU, and I guess back at DDN now, because he did some of this original work back on the Lustre 1.4 system. Eric Barton, Andreas Dilger, Robert Reed, who listened to me blather about this and tell me when I'm going completely off track, and the technical working group of OpenSFS and the board of OpenSFS. And I'm open to any questions.
Questions?
NDT need to this mapping for security checks, but what the reason for OSS no?
I'm sorry, I have problems hearing. Can you repeat the question?
In your presentation, you say UID mapping is done on OSS nodes, on MDS node, and MJS nodes.
Yes.
But primary reason for UID mapping is security checks, and these security checks performed on MDT only. So it's question why it need for other nodes.
Oh, why am I doing it on the OSS nodes as well?
Yes.
Okay.
Microphone, bro.
Oh, sorry. Dude, sorry. I'm doing it on the OSS nodes, the security check, because I want to ensure the integrity of the data. And I need to ensure the integrity of the UID so that I'm properly doing the UID mapping, and if you have quotas turned on, that I'm not basically allowing you to inject data as a third party into the file system. Or
OSS don't provide additional security checks for bulk data. So we don't able to check security UID of user which is in a bulk request.
oh, why am I doing it on the bulk request?
So
I'm
this is
just a
will be not.
I'm going to do integrity checks on the bulk request and authentication of the messages, but I'm not actually.
But it is done not dependent of nodes currently. It is part of Kerberos layer SPT layer PC.
Oh, okay. Huh.
So, Alex, one comment. It's Andreas over here.
Okay.
So the UID mapping has to be sent to the OSTs. Well, you said per quota because the objects, when they're first created on OSTs, don't have a user associated with them at all. It's only at the first write that the user ID gets associated with the OST objects. But also, once we get to distributed namespace, you're going to have multiple MDTs, and you're also going to have to distribute the UID mapping between the MDTs, right? And so it makes sense to have a centralized mechanism to distribute that.
But anyway, this will be sent from MDT connected to this OST. So no from mapping for client for PC.
It's the client that sends the UID to the OST to identify the object the first time it's written, right? So there's no additional, there's a pre-create step that creates ownerless objects on the OST. And it's only later on when the clients write that they add a UID and GID to the OST objects. So that isn't the protocol that happens between the MDT and the OST. It comes only from the clients.
All right, so what I'd like to see is for you guys and Josh to talk.
Yeah.
But not right now. Thanks, Josh.
No, thank you.